Okay, I'm going to share the screen. Okay, so there we go. All right, so what we're going to discuss today is we're going to continue with performance metrics. Oops, sorry, I'm in the wrong class. Let's go to 365. Hey guys, content. All right, and we should be around here and here, right? These two modules. So today I'm going to wrap up performance metrics. So if you remember last week, I went over like the first half of those slides, kind of gave a quick intro, and then I said we're going to do an example of the same ideas this week today. So I'll start with the slides here, and then after that, we're just going to get into these links basically and start coding once again in the familiar environment of Anaconda and everything, just like we did in NumPy. So the only new library we're going to add is PyTorch, basically. All right, so let's begin with the performance metrics. I'll download this file. We are recording and sharing. So we were talking about performance metrics. There are many performance metrics, as you have used these performance metrics already. When you did your WECA assignment, you had regression problems and you did R-square, right? And then you had classification problems and you used precision, recall, F measure, right? And F1 score. Remember that this sequence of neural networks ends with the SciFAR 10 competition, and you will use those performance metrics to determine how good your models are. So just a quick recap. On Tuesday, we went over these slides and we talked about basically the confusion matrix and its relation to all the metrics of precision, recall, accuracy, F measure, etc. Okay, and today, so now we're going to go over, round two, an example, basically a case. Okay, so I'll go through this. Hopefully you've had a chance to read it. It's a kind of like a system, right, that you're trying to build for homeland security. Okay, so let's go over the scenario, and then let's just think about the metrics. Okay, and hopefully this underscores why accuracy is actually not a good metric for classification. Remember, this is only for classification problems. Like when you have labels like Setosa, Virginica, or Sequoia. So the kind of the scenario or the problem, the case starts with, would you believe someone who claimed to create a model to identify terrorists trying to board flights with greater than 99% accuracy, right? If you had data, right, like this one, you could build a model and it could say that it has a 99% accuracy. But that actually doesn't have any meaning, right? 99% accuracy in this case does not tell you any, it does not mean that the model is good. Okay, so well, here's the model. Simply label every single person flying from a US airport as not a terrorist. Given that 800 million average passengers on US, fly on US on flights, right? Given that 800 million average passengers are on US flights per year, and then we only have 19 confirmed terrorists who boarded US flights from 2000 to 2007. So this is an example of a highly imbalanced data set where you can see we have 800 million samples of one class and just 19 of the other class. You see that? So obviously in this model, if we just label everyone, right, as not a terrorist, then the model has 99% accuracy. It got, this group correct. But really what we care about is the 19 terrorists. Do you see that? And so this is why we have to drill down into the other metrics. So this model achieves an astounding accuracy of 99%. It sounds impressive, but basically this is not something that anyone would buy from. Okay, and if you understand the metrics. While this solution has nearly perfect accuracy, this problem is one in which accuracy is clearly not an adequate metric. Okay, so the terrace detection task is an imbalanced classification problem. We have two classes, terrace and not terrace, with one category representing the overwhelming majority of the data points. This is a difficult problem, by the way, really difficult, okay? And it's, you know, there's no easy solution. Basically, sometimes here, I mean, you have to try a lot of things, but you could build a model where you just have 19 terrorists and 19 non-terrorists, and that would be called undersampling, which basically means you would drop a lot of samples, right? So you balance it, but then that may not be such a great model, but it's an approach, okay? The other approach might be something called oversampling, where you basically take the 19 terrorists, kind of average them, and then take that average, add some noise, and create new samples called synthetic samples. So the idea is that they would be similar to the other 19 terrorists, statistically speaking, and you can create many synthetic samples. While you can balance the data set, that's probably also not a good solution because those terrorists didn't exist. So you're kind of like fictitiously creating.
What would be a good approach?
I can't tell you. I mean, work the problem.
Get more terrorists.
Get more terror. Yeah, exactly. Get more terror. Actually, that's a very correct answer.
But like,
go to other airports.
okay, but like,
But yeah, you're very right.
okay, but like,
Yeah,
if you go to the previous slide, well, how many people?
800 million.
800 million.
And
How
only
many
19.
And how many terrorists do we need in order to balance out that data set?
800 million.
800 million, okay.
Do you see the problem? I mean, this is an exaggerated example, but actually, if you're Homeland Security, you probably would want this, especially after 9/11 and all that. They would have dumped $1 billion on this problem, right? So the key is this is difficult. Okay. So the point of this case in your solution is actually the right one. The point of this case is not how do we solve this, but just to look at the metrics and what information they provide. Okay. In this scenario. So we talked about how accuracy would not be good. So instead, we just have to look at precision and recall. Another imbalanced classification problem occurs in disease detection when the rate of disease in the public is very low. So it's a similar idea. And maybe in your stats course, you probably looked at something like that. In both these cases, the positive class, disease or terrorist, is greatly outnumbered by the negative class. These types of problems are examples of the fairly common case in data science when accuracy is not a good measure for assessing model performance, okay? So that's why accuracy is not the metric that you should use. You know, the conclusion kind of these slides is to use the F measure instead, right? And that's kind of what this is wanting to demonstrate. So intuitively, we know that finding all negative data points in the terrorist detection problem is not helpful. And instead, we should focus on identifying the positive cases. The metric, so that's why I was saying, okay, then just use 19 good ones and 19 terrorists. You have a balanced data set. But then that's going to create a lot of like false positives, basically. Yeah, go ahead.
Well, another issue could be as well is you're not applying the same distribution because you're training your model on different distribution.
Yeah, different.
And actually, it's applied in the real world. So wouldn't that throw everything off too? Like there's not like there's not like only like there's not like the ratio between terrorists and regular people is probably like way off compared to like I guess what I'm asking is like wouldn't that also have a bunch of issues too?
What would?
By like taking just 19 regular people and then 19 terrorists.
Yeah, you could also, okay, so you're just taking so you're missing information. I think is what you're trying to say, like yeah, you're losing information. What you might want to do is take the 800 million, calculate the distribution, and then extract 19 synthetic ones from that.
Gotcha.
You can make up the ones, but they're not real. You're making them up. So these are just approaches. I can't tell you what the right answer is. You know what I mean? Yeah. No. This is a hard problem. This is a very hard. Go build this and you'll become very rich, right? You know, it's kind of how it is. Yeah. So guys, questions? All right. So intuitively, we know that finding all negative data points in the terrorist detection problem is not helpful. The metric our intuition tells us we should maximize is known in statistics as recall, or the ability of the model to find all the relevant cases within the data set. That's really what we want, right? All the 19 cases we would want to find. So we saw this metric before in the previous set of examples. So recall is basically the true positive. So you can see it, everything is always in terms of the confusion matrix. So recall is going to be the true, for the denominator, the true positives, which is this one, plus the false negatives, right? So it's these two. So out of all the real, how many do we get? Do you guys see that? That's basically it. Okay, so the metric just looks out of all the reals, the 19, how many are we able to? Do we get the 19? Then we have really great recall. Okay, the problem is sometimes when you maximize to get all the recalls, you're going to end up getting a lot of these false positives over here, right? So it detects, it's going to predict some ones that it shouldn't predict. So people that are not terrorists are going to be marked as terrorists, but you end up finding all of them, right? So that's kind of the trade-off that you have. You have to balance out both precision and recall. So if we go over the definition here, so the precise definition of recall is the number of true positives, which is this one, divided by the number of true positives plus the number of false negatives. Okay, so all the real cases, the actual cases. True positives are data points classified as positive by the model that actually are positive, meaning they are correct. And false negatives here are data points the model identifies as negative that actually are positive. So these are the terrorists it missed, correct? Right, and you can see that here. So that's why it's the actual. In the terrorist case, true positives are correctly identified terrorists, and false negatives could be individuals the model labels as not terrorists that actually were terrorists. Okay? Recall can be thought of as a model's ability to find all the data points of interest in the data. Okay, and you can see that basically the formula here. True positives divided by true positives plus false negatives, or in terms of the terrorist example, terrorists correctly identified divided by terrorists correctly identified plus terrorists incorrectly labeled as not terrorists. You guys see that? That is recall. Okay, and it's the same definition that we had done before, only this uses the familiar true positive, you know, false positive, false negative, true negative that you see a lot in other courses like your stats. So how can we find all terrorists, right? In this case, let us predict everyone is a terrorist and problem solved. We find all of them, right? Well, recall will be high. That's true. The problem is, in the case of recall, when we increase the recall, we decrease precision, right? Again, we intuitively know that a model that labels 100% of passengers as terrorists is probably not useful because we would then have to ban every single person from flying. This approach would suffer from low precision, right, which is the other metric, or the ability of a classification model to identify only relevant data points, right? So now we're going to look at precision. Okay, so precision in this scenario is defined as the number of true positives, this one, okay, divided by the number of true positives plus the number of false positives. So here, so now it's out of this one, which is the predicted, right? So out of the predicted, how many did we get right? Do you guys see that? So one is this one, and this in precision is this one. So recall is the what is it, vertical, and then precision is the horizontal, right? Does that make sense? So one goes up, the other goes down, right? You have that problem. Now, sometimes I should say, sometimes the metric you want is precision, and you don't care, right, about, you know, even if you have bad recall or the other way around. This can be a scenario, right? You're looking for certain information. You don't need all the cases. You only need the cases that you get to be relevant, for instance. So that's one possibility. Yeah, go ahead.
Like in the case of the terrorists,
Mhm.
you probably don't care as much about false positives as much as false negatives, right? It's like, hey, like, oh, search this person, he's terrorist, he's not terrorist, versus, oh, this person's fine, he actually is terrorist, right?
Well, it depends. I mean, so what you care about is finding the terrorists, obviously, but you also don't want to search every, whole bunch of people.
Right, not too, I guess, like I was saying.
Because if you're, that's resources. That's like an FBI agent
Right,
sitting down for a week. That's a resource that's being wasted.
where I guess like what I was saying is like in that example,
Uh-huh.
right? The false positives aren't the same as false negatives. Like you probably care much more about the false positives, false negatives than false positives.
You care more about the false.
As in people who are like,
Say which one though, because
I'm sorry, so like, you probably care more about getting all the terrorists.
you care about getting all the terrorists. The problem is, in this scenario, the more you get terrorists, the more you also get people that are not terrorists that will be flagged.
Right.
And that's also a problem. I get what you're saying, but in this scenario, that's expensive.
Right.
That's like a lot of people that you're stopping at the airport. Like, I'm not a terrorist, and you're gonna put them in a room and they're gonna sue you.
Like grandma like stands or something.
Yeah, some grandma, take her pills or something. You know what I mean? It's a big issue. This is important. Now, there are some cases where, like if, and this is actually an example of cancer detection, right? So you find all the cases, right? And then you have a follow-up exam to rule out, but you don't want to miss anyone because that would mean that the person could die. You see that? All right, so precision is defined as the number of true positives divided by the number of true positives plus the number of false positives. So this one here, out of the predicted, how many did it find? That's the precision. False positives, these here, are cases the model incorrectly labels as positive that are actually negative. In our example, individuals the model classifies as terrorists that are not, okay? Precision expresses the proportion of the data points our model says were relevant and actually were relevant, basically. It's what it detects, okay? So you can see that here, precision, true positives divided by true positives plus false positives. And in the case of the terrorist scenario, terrorists correctly identified divided by terrorists correctly identified plus individuals incorrectly labeled as terrorists. So you have both of these cases. Now we can see that our first model, which labeled all individuals as not terrorists, wasn't very useful, the accuracy. Although it had near perfect accuracy, it had zero precision and zero recall because there were no true positives. Now, if we can modify the case, so say we modify the model slightly and identify a single individual correctly as a terrorist. Now our precision will be 1, no false positives here, okay? But our recall will be very low because we will still have many false negatives. So remember that it's almost, you can view it as, this goes up and this goes down, or this goes up and this goes down, right? So it's like you have that balance, okay? So that's the problem. If we go the other extreme and classify all passengers as terrorists, we will have a recall of 1, false negative 0 here. We'll catch every terrorist, but our precision will be very low and we'll detain many innocent people. You see? So that's basically the problem. In other words, as we increase precision, we decrease recall and vice versa, okay? So we need to find a metric that balances out the two of them, okay? And that's why we combine precision and recall in one metric called the F measure. In some situations, we might know that we want to maximize either recall or precision at the expense of the other metric. That's fine. For example, in preliminary cancer screening of patients for follow-up examinations, we would probably want a recall near 1. We want to find all patients who actually have cancer, and we can accept a low precision if the cost of the follow-up examination is not significant. So this assumes that we're gonna, do a second exam. However, in cases where we want to find an optimal blend of precision and recall, we can combine the two metrics using what is called the F1 score. You guys see that? So this is why this is the metric that is usually used in machine learning, because this one will balance out both of these two metrics. So here's the F1 score. The F1 score is defined as the harmonic mean of precision and recall, taking both metrics into account in this equation here. The intuition of F1 can be seen here. We use the harmonic mean instead of a simple average because the harmonic mean will punish extreme values, okay? So the idea here is a classifier with a precision of 1 and a recall of 0 has a simple average of 0.5, right? You guys see that. So if you have recall of 1 and precision of 0, the average of that is 0.5, right? But the harmonic mean of this, which is the F1 score, would be 0, okay? So that's why you use this one, because you don't want to favor one or the other. So the F1 score gives equal weight to both measures. And there are other metrics available, basically. So F1 will be the most common metric used in machine learning. If we want to create a balanced classification model with the optimal balance of recall and precision, then we try to maximize the F1 score. Any questions? You guys get the basic idea? Yeah, questions? Nope. All right. So yeah, so this is just an example. I suggest you read through it, okay? You can think of this problem in multiple scenarios, like in health and things like that. But that's the basic idea. Okay. All right, so those are the metrics. We went over the function already, right? So I think I gave you this function. This is the function that you can use to evaluate your classification models. So in essence, the best practice is usually just to print all the metrics: precision, recall, F measure, and the accuracy, plus also the confusion matrix. In general, you'll use the F1 score, but in some scenarios, you may want to use precision or recall instead, okay? For regression, if you remember, we had talked about these metrics. So we have the RMSE, which is a root mean squared error. We have R, which is the correlation coefficient, which is the metric that you guys used in WECA. And if you remember, we had the R square, which is the coefficient of determination, right? So you've used this. Remember that the previous metrics were for classification, and these metrics are for regression. Some ideas about R square. So R should have a range from -1 to 1. R square should have a range from 0 to 1. An R equal to 0 means no correlation, bad model. An R of +1 means good positive correlation. An R of -1 means good negative correlation. And that's fine too. With R, close to 1, either positive or negative is good. R square is preferred it's usually a metric that a lot of people use. The R square is just R squared, R times R. R square gets rid of the negative, and it is the preferred metric. So basically you compare all models, and the one with the highest R square is the best. And this is what you guys already went through with your project. RMSE, for just one model, it tells you very little, but when used to compare between models, it is useful. Since it is an error, with this metric, you select the model with the lowest RMSE. All right, and that's it. These are the basic performance metrics of machine learning, like of the simplest models that you have for either classification or regression. Does this make sense, guys? Are there any questions? Questions? All right, so this is what we're going to be using to evaluate our machine learning algorithms, okay? All right, so now that we've finished these slides, we're going to go ahead and get back to the idea of the duality of neural networks and the matrix multiplication. Okay, so I will go over, basically, hopefully you remember that lecture, and I'll go over an example now using Python. Go ahead. I'm going to need to start the Anaconda environment for this. So I'm going to do two examples. The first one is that iris example that I did on the board, on the whiteboard. All right, so let's go ahead and get started. All right, so I'm going to start the so we're going back to Anaconda basically. So the Anaconda prompt. EIR, the desktop, EIR, CITS, 365, 2024, EIR. All right, so this is where we're going to begin. So today we're going to do 3 scripts. We're going to complete 2 for sure, and we'll start the XOR one. I don't think we'll finish that one today, but that's fine. All right, that will be your first introduction to deep neural networks, and at the end of that code, you will have a deep learning model, right, for the classic XOR. So we're going to go through all of this today, or start this today, the basic pipeline. Okay, so I'm going to need an environment. So I'm going to go to Conda environment list. All right, so I think we were using Py37 365. Conda activate Py37 ITS 365. All right. I'm going to create neural nets. We are, basically building neural networks now. All right, so we're going to start, we have the environment here, so I'm going to start a Jupyter notebook. All right. And we're going to create our first script. This will be the one that I said, like the duality, right, of neural networks and matrix multiplication, basically. So it's very short and simple, but it's what we did in the slides in the lecture last week. So I'm going to go ahead and create a notebook. Okay, I'm going to give it a few cells. I'm going to call this one nn x w x w b. matmul. So if you remember, it's, we perform a matrix multiplication. We went over all the ideas, remember, of how to multiply two matrices. We went over the process and everything. So this is what I'm going to cover now. Okay, so I'm going to rename it. All right, so we're going to, in the past, we've done everything in NumPy. As I said, NumPy, is like the original framework, and then PyTorch and TensorFlow, which are frameworks for deep learning, have been created kind of to be like NumPy, a lot like NumPy. So they're very similar. All right, so we are now going, instead of using NumPy, which we can have available if we want, import NumPy as NP, right? So I'm going to bring it in, although instead of using NumPy, I'm going to use Torch. So I'm going to say import Torch. So this is PyTorch, okay? PyTorch is, as I said, the library that we're going to use to build neural networks, deep learning, etc. All right, so first we have to check to see if this is installed on this machine. So I'm going to hit run. All right, I have it available. I don't know if you guys have it available, but if you don't have it available, you would do something like pip install Torch, run that, and that should be enough. Okay, any questions? All right, so not hearing any questions, so I assume everyone has Torch. All right, so now let's go ahead and think of the problem. So we want to do a matrix multiplication. If you remember, we were multiplying x times w, right? And we just want to look at the shapes of this. Okay, so how do we do that? So I'm going to create the x tensor in this case. I'm going to use torch. So I'm going to say torch dot random in, and I'm going to create it as a tensor of 150, comma 4. You guys see that? And then I'm going to print the shapes. So x dot shape. Do you guys see that? So what does that look like to you? Looks like the iris data set, right? The iris data set has 150 samples and 4 features, correct? So it would be the data. Think of iris. This is why I modeled it like this. Obviously, the data inside is random. It doesn't matter right now, but what matters is the shapes, right? And we're going to do the operations. And I want to show you that I'm going to do some multiplications. And at the end of the day, what I'm doing is building a neural network, okay? Just by doing some multiplications. So I have 150, comma 4. Then on last week, we said that basically a neural network has the basic function in its simplest form of what? Of a line, remember? And what was that formula? M times X plus B. Do you guys remember this? This is the formula for a line that you learned, in high school. And actually, that is the formula for a neural network in its most basic form. We build from this, complex neural networks. But this is the idea. Okay, so what we need is we want to do a transformation of X, right? By multiplying it times a W, I'm going to change the variable to W to produce another output, another representation of the samples. So in the example that I did on, and I'm going to need the board for this. I forgot to set it up. Forgot that I needed to draw that. All right, so let me try this. I'm going to open the whiteboard. Okay, pencil works, thankfully. All right, so if you remember on last week, we built a neural net, right? And we did this. It was basically a neural network for iris. It was a multi-layer perceptron, right? So I had 4 neurons in the input layer, right? This is the input layer. And then I said that I wanted to have a hidden layer of a neural network that had 6 neurons, right? Do you see that? And basically, we needed to have all these connections here, and this was called W0, right? And then after that, we want to build a model that predicts, because this is iris, we have an output layer. We have an output layer where we have the classes, Setosa, Virginica, and versicolor. Do you guys see that? And here we need to have another set of weights. We're going to call that W1. So this is how you usually draw neural networks, right? But the thing about this is that basically these are just simple matrix multiplication, okay? And they're basically, you can think of them as transformations from one vector space to another vector space. And that's kind of the idea that I want to see if you guys can like picture from today's lecture, okay? So in a neural network, we just define, even though we have 150 samples, we don't have to specify that in the neural network. We just specify the size of each input, which is 4, okay? And then each sample is going to be converted. So you can think of this as being from the point of view of just one sample. So each input sample has 4 neurons. We're going to transform it by doing a matrix multiplication into now a representation that has 6. And then after that, another matrix multiplication for it to have a representation of just 3. But what we're saying is, I want you to tell me out of this vector of 4, which one of these classes it is. Do you guys see that? Does that make sense? That's what a neural network does, right? A neural network, you give it, you know, an example of a flower, iris, and it's going to tell you whether it's Setosa, Virginica, or versicolor. Got it? All right, so let's go ahead and do that. Let's do these transformations, okay? So another way of thinking about this is I have a vector space R4. I have my sample, you know, sample 1, and I'm going to put that point in a vector of 4. Do you see that? Like that, imagine, right? Then I'm going to multiply times W, right? And produce, so this is the input. I'm going to multiply times W. Now I get the hidden layer, and sample 1 now becomes R6. Do you see that? It's like I took that same point, but now I put it in another space. But this is the space represented by these 6 neurons. And I'm denoting it R6. So this one would be a space of 1, 3, 4, 5, 6. And now somehow the point appears there. Do you see that? The idea is, the important thing is the weights need to learn a way to put the Setosas here, the Virginicas here, and the versicolors here, so that this is easy to divide, to split, right? So that's what it's trying. It's trying all these spaces, right, of size 6 and putting the points there so that they're easy to separate. Right, separating lines. All right, and then I'm going to take the sample S1, which is now in a space of 6, multiply it times another set of weights. And what do I get now? It's in space 3. Do you see that? Because now it's going to be represented by a vector of 3. So now it's like that. And that's it, basically. Do you guys see how there's like a vector space analogy going on here? Okay. So let's do this now in code, all right? And hopefully, you know, the values don't matter because I'm not learning weights. But what matters is that I'm going to be multiplying this times weights to produce this, and then this times weights to produce this, okay? And hopefully that'll make it a little bit more obvious, okay? Stop me if you have any questions. So let's go back to the code. So now I'm going to hit here, share the screen. All right, so I've said to you guys that really a neural network starts here. This is like a linear mapping, or the basic operation map mul, okay, the matrix multiplication that we did on Tuesday. So I also need W, right? I'm going to then, I'm going to just put a comma in here. And now I'm going to need a W. I need to define what this W is. And then I'm going to do a matrix multiplication. So I'm going to do here y equals torch dot matmul. Notice it literally is matmul for matrix multiplication between x comma w. Do you see that? So I'm multiplying these two to produce a new representation, okay? Now I want y to be of shape. So I want y to be of shape 150, 6. That's my objective, okay? Because I'm mapping every single one of the 150 samples that are here of size 4 to this new space of size 6. So then the result should be 150, 6. Do you guys see that? All right. So the question is, how do you define the weights, right? So you need to define this. So you then can do this matrix. So I'm going to do torch dot rand n 4, 6. You see that? That's the weight. So I'm going to print shape, w dot shape, hit run. It's 4, 6. Now let's go back to the neural network. We had looked at this before. What did we say? To create W0, if we look at the diagram, we have to, we have to connect, right? It's going to be fully connected. We connect all the neurons. So basically, all those connections are in a little table, W0, which has 4 rows for the 4 X values, input values, and 6 over here for these 6 neurons. You see that? So that's basically the size of that, which corresponds to the neural network. And if you look in the previous example, that's exactly what I created. It's a W matrix 4, 6. All right, so let's try that out. So now I have my X of size 150, 4, which is the data. I have these weights, which currently they're random data, but this is what in neural networks you have to learn. You see that? We have to find the right set of values that will give us what we want. Now that we have the weights and the X's, we can go ahead and perform the operation. So I'm going to do dot, torch matmul X times W, and I'm going to print the shape. So if I run this, notice it is now 150, 6. So I have effectively taken the 150 samples and I've converted them from being vectors of 4 to vectors of 6. Do you guys see that? That's it. That's a neural network. The key part of this is, obviously, in X, we would have the actual data, right? This is iris data, the file that we get from iris. And this W is something that we need to learn. And that's where machine learning comes in, deep learning, the procedures, stochastic gradient descent, etc., to learn the appropriate weights, right? The appropriate values that go in this weight matrix so that when we multiply this times X, you know, we get the correct values that will help us to classify our samples. All right, so let's take this a step further. So if we go to the, we have now the matrix Y. So now I'm going to change this actually from Y to what? To hidden 1, right? Hidden 1. Okay, so it's still 150, comma 6. So hidden 1 now, I'm going to go back to the whiteboard. So effectively, I take the x's, multiply times the w, and I'm here at this point in time. So I am here, basically. Now I want to move further and predict the class for each one of these samples. So I need to do what? I need to take this H1, multiply it times W1 to obtain output. Do you guys see that? Which output could be Y in this case. And that's a neural net. I'm not including the bias here, but the bias is something that you could also add easily. So let's go ahead and do that. So now I'm going to perform this operation. Okay, so I'm going to add a few more cells. Okay, so I have this. So now I need W1, which needs to be of some dimension. I'll have to think about that one. Okay, some dimension. And once I have that, I'm going to do the matrix multiplication. So I'm just going to copy this. Now I'm going to map mul H1. I'm going to do the matrix multiplication between H1 and W1 to obtain Y, the final result. And we know from the neural net architecture that what we want is we want the shape of Y to be what? 150, comma, what? 3. Because for each sample, we want to predict a vector of size 3 so that we can select one of the labels, either Setosa, Virginica, or Versicolor. That's a neural net, just these simple matrix multiplications. Okay, so so you guys help me out, right? So this part, I kind of use your knowledge. Okay, I'm going to copy this operation. I need to know the dimensions of W1 so that I can get 150, comma 3. So what should we try here? What do you guys think? 6, comma 3. Very okay. Nice. All right, so we are at W1. 6, comma 3. Okay, let's print the shape of that. Okay, 6, comma 3. Do you guys see that? That's the thing you're afraid of that's gonna end humanity. Just some simple matrix multiplications, right? That's a neural net. That's it. I mean, there's a few additional things, obviously, right? But in essence, this is what you're doing. This is the feed forward, right? So you're starting with some data over here. Iris, you know this file. It's got 150 samples, 4 features. Multiply it times some W's of the right dimensions so that you can map every single one of those samples now to a space of 6. You can map it to a space of 100, space of 1,000, whatever you want. You can keep doing multiple layers of this, keep going and going and going, making it deeper, 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 right? You can create any architecture that you want. And then here, once we are at that hidden 1, we just created, because we knew, right? We know what we want. So we know what dimensions we need in the W1. And then the intuition here is, remember, 150 by 3. So it means that we have the 150 samples by 3. we're going to have values in each of those columns for each sample, right? And the goal is that you should have there, let me do this, probably it's easier on the board. The goal of that last part right? So now we, in the last part here, we do this, that, and in this part where we created the 3, we're basically saying that we have the 150 samples, and then here we have, let's say, C1, C2, C3 for class. We just saw the shapes. We literally got this matrix as the output. But the intuition is this is sample 1, sample 2, sample 3. Currently, these are random values, right? Random values. But when we start training, what are we going to do? We're going to have labels. So the model, give it an input, given some weights, predicts, right? Initially, these are random values. It's like 0.2, 0.3, 0.5. You see that? But we're also going to have the real label. And the real label will look like this, guaranteed, right? Because it's only one class, either Setosa, Virginica, or versicolor. So that means one of the classes will be a 1 and the other ones are 0. In another example, 1, 0, 0. Do you see that? This is what we have. So we go forward with those matrix multiplications, and for each sample, we arrive at 150 by 3. Now, remember, we're multiplying times these weights, and that's the critical thing. These weights is what changes. So we have one set of weights. It produces 0.2, 0.3, 0.5. We compare it to this, and the idea is that this should have been the highest value because this is the highest value. Do you guys see that? So that's what the error that you're going to try to minimize, if that makes sense. Okay, so here you would say, okay, those weights are not good because this value here is the highest, but actually it should have been this one. So what do? Try a new set of weights. Do you guys see that? A new set of weights, perform the matrix multiplications. Okay, perform the set of matrix multiplications, and now you get 0.1, 0.1, 0.80. Do you see that? So now, what do you say about this set of weights? For this example, these weights are better than the previous weights. Why? Because when you compare this to this, you minimize the error. You see that? Guys, this is actually 0.8 is close to 0.1, right? And these 0.1 and 0.1 are close to 0. So that's the whole objective of machine learning. You perform these matrix multiplications to obtain this matrix, and then you compare it to the real ones, and from there, you update the weights accordingly using a set of algorithms called backpropagation. That's something I haven't covered, obviously. I'm only right now showing you this part. Any questions on this idea? Nope. Is this clear? Yeah. All right, great. So this is basically, ask questions, right? Play with this, but this is literally what's happening in neural nets. You're always performing this matrix multiplication, okay? And we're gonna continue to do tricks, etc., to improve these results even further, okay? So another scenario here, let me move this over here. Obviously, you're gonna run several examples at a time, so you're always calculating the performance out of all the samples that you provide to it, not just one, right? So we're gonna be looking at this one compared to that one, this one compared to that one, this one compared to that one. It's a type of a distance function, right? And our goal is to minimize that distance because when it's minimized, it means basically that we would predict something like 0.01, 0.01, and 0.98, right? And that would be the closest probably that we would ever get to this. See that? So we may never achieve 0.10, but we can get pretty close to it by obtaining 0.01, 0.98, and 0.01. So this is when the set of weights that we have selected for the matrix multiplication is starting to become very, very good. All right. Well, all right. So that's the intuition for this. Okay, so let's go back to the Jupyter Notebook. So you can see we've done the operations here. So what is then a deep neural network, right? So here we only did an input, a hidden layer, and an output layer. Now I want a second hidden layer, right? So how do I achieve that? Well, let's think about it. Let's go to the whiteboard. Okay, so now I'm going to use the same example of iris. I have 4 here. I have 6 here, right? One more. 6. And I still need 3 in the output. Actually, let's do 2 hidden layers. So now I'm going to add another hidden layer and another one. Okay, how many neurons do I put in this one? Let's make it fun. Let's do 10. 5, 6, 7, 8, 9, 10, right? That's 10. Seems difficult. How do I do that, right? Well, it's the matrix multiplication, right? So just figure out the shapes, build the architecture, and then you train it basically. And then this one, let's do 5. Okay, so this is what I'm going to do in matrix multiplications. Okay, I already have, we're going to label them. So this is H1, H2, H3. This is the input, and this is the Y predict. So I've already done this one. I know that works. I already did this one. I already kind of had the last one, but now I need to do this, right? So I'm going to do the H2 one. Okay, that's 10. So going back, okay, so I'm kind of 156, right? So this is where I am. Okay, so I'm going to delete these so I don't get confused. All right, so now the next layer is going to be what? H2 torch dot map mul. And I know now I'm going to multiply. I'm going to need a W. I'm going to call this one W1. Let me be consistent here. Since this is H1, I'm going to say W1. 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 Okay. So then this is going to be W2. I'm going to need to define the size of that. W2. Okay. And the input to this is going to be H1, right? So H1. So then I'm going to do H2 dot shape. My objective is that I should have 150, 10, right? 150, 10. So I need to define the shape of W2. So I'm going to do control copy. All right, so let's go ahead, run this. 150, 4, W1, 4, 6. When we do the matrix multiplication, 150, 6. That's where we are. Now we need to convert this into 150, what? 10, 150 comma 10, right? So that's, so how do we do that? We need to define, oops, sorry, 150 comma 10. So 6, 10. You guys see that? So if we do that, 150 comma 10, I have effectively taken the 150 samples and mapped them to another space, a space of 10 dimensions now. That should be this one here. You see that? That's basically, that takes me in the neural network to this part. Then I'm going to go another layer. Okay, I need yet another weight matrix so that I can multiply this times that weight matrix and transform those samples into the other space. This is going to have 5. Okay, so I'm going to do that. This is hidden layer 3. This is a deep neural network of 3 hidden layers. And basically, you just have to do this with matrix multiplications. So let's go ahead and try that. Okay, so now I'm going to need to define the next hidden layer, H3. That's going to be torch.matmul. Okay, the input to this is H2, correct? H2. And we need to multiply it times W3. We're going to need to define W3. So that's going to be torch.rand n. What are the dimensions of this one? This is architecture, and you will have to, you won't do it like this, but when you build neural networks, you will have to define these values. Someone had their hand up?
10,
Yeah. 10 comma 5. Yeah, that's it, right? So you map from one to the other, and basically you're just doing these matrix multiplications. You won't see this again. This is I promise you, this is the last time that you'll see it in this form. But I want you to understand that this is what you're doing behind the scenes, okay? So this is going to be 10 from one neural network layer to the next one, which is 5. And that should give us H3. So I'm going to print the shape of H3. Okay, so let's do that. 150, comma 5. So now we are in the hidden layer 3 of the neural network. Oh, I'm gonna go back to the whiteboard. So we are now here. Think about that. In just those few lines of code, you built a neural network. It's not, it's a linear neural network, not a non-linear, because we still need to add that in, but effectively you are building a linear neural network, a deep neural network. So now the final part is mapping all the samples in this space, R5 to R3, where now that sample is now that results in the prediction for the specific sample. All right, and that should be the last layer. So I'm going to hit stop share here, go back to share screen. So, hopefully this is now pretty easy for you. We're going to call this Y torch dot matmul. Okay. This is going to be H3, the data from the last hidden layer, right? Times, let's call it W4. You see that? W4. And so we define W4 as, okay, we're going from 5 to 3, right? So it's going to be torch dot rand n 5 3. You see that? That's it. That's how you build the architecture so that the data flows. So now, oh, and then we're going to print a shape. There you go, 153. So you've taken the initial 150 samples, you ran them through this neural network, and you transform them basically, just by doing these matrix multiplications. All right, any questions? All right, hopefully that made sense. So I think now we're gonna get into building our first neural network. We're gonna build the classic XOR problem to kind of motivate what neural networks are. Remember, this is a linear. The way that I'm doing this right now is a linear set of transformations. So I would actually, with this approach, would not be able to solve XOR. I would need to add some additional components, right? And convert it into an actual neural network. So that's what we're going to do now. I'm going to create a new Jupyter notebook. So I'm going to save this one. This is already on the GitHub, so you can take a look at it. So now I'm going to create a new Python. Okay. Okay, so we're going to import Torch, basically. All right, so what do we need for this problem? We're going to need some data. The data will be here, will live here, and I'm not going to read it from a text file. Instead, we're just going to create it here. It's going to be the XOR data. So we're going to need the XOR. This will take a while. So, okay, we're going to need the XOR data. We're going to need to define the neural net, so the architecture of the neural network. Okay, so we're going to have to learn how to do that. So the first thing you need to learn is that the operation y equals w times x plus b, right? This operation that we just saw is something that you don't have to hard code like this in PyTorch, but instead you just use a function called nn.linear, okay? So this is the function that we're going to use, nn.linear, but I want you to remember, please, that whenever you invoke nn.linear, what you're doing is this. So I don't want you to forget that, because it's very easy to forget since, you know, we're just going to be using nn.linear. Does that make sense, guys? All right, so let's get started then. All right, so the way that we're going to write our PyTorch models is going to be object-oriented. Okay, so you just got to, initially that might seem like an overcomplication, but eventually it pays off. All right, so we're going to learn a basic template that we're going to use to define our object-oriented classes for our models. Okay, let's go ahead and get started. Okay, so we're doing, so we're doing the XOR. We're also going to do iris. All right, so first thing we're going to do is just build a multi-layer perceptron. Okay, so go ahead. I'm going to add a comment here. First, neural network architecture. MLP. Okay. Okay, so the way that you do this is we're going to need a library, import torch. Then we may need some additional components. So we are going to need so three things usually: import torch .nn as nn. This is basically the module that brings in pretty much everything that we need, all the neural network objects, such as nn.linear, right? We're going to get it from here, okay? We also can use, can have available import torch dot nn dot functional as f. All right, this is basically what we're gonna use to actually get the loss functions and things like that. And the third one that we usually use is from torch dot optim as optim. And this is for the optimization functionalities in function space. Okay, so these are the three main libraries. There's many more, but these are the three main libraries that we're going to be needing. Got it? Okay, so now let's proceed to look at the basic template. I always use this. Always. Whether I'm building a linear model, a linear regression, or a neural MLP, or a deep learning algorithm, or CNNs, or a transformer, I always use this template, okay? All right, it makes it, you know, if you're consistent with this, you know, it'll become easy for you to code to the point that you don't always have to go and like copy some code. You can actually literally write it, okay? So so we have these three libraries. Gonna hit run. So it's thinking, it brought in the libraries. Remember, we still need to bring in the XOR data. But the first thing I want to show you is the connection between what we just did, which was the matrix multiplication map mul, and how we define that in the, you know, in our code. This is like critical, I think, in my opinion. And so I want to do that first. All right, so let's build a multi-layer perceptron. So I'm going to add a comment here, MLP. Remember, an MLP has an input layer, a hidden layer, and an output layer. So Python object-oriented programming lets us use the keyword class to define our class. So I'm going to call it MLP underscore net. We are going to be using extensively class inheritance. So that's something that you just take advantage of. So that means that we are going to inherit from nn something called module. By doing this, we basically can create our own model classes using the PyTorch default nn module for neural networks, okay? So this is just class inheritance. So I'm going to go ahead here, and now inside this class, we usually have at least two functions, but we can have a third one as well. I mean, we can have more, but usually in general, you have two, and it's also okay to have three, or common to have three, but you can have way more than that. But the two that you always want to have are the following. So you want to have the constructor, which is the init class, init class, okay? And that's usually denoted by def underscore underscore. So there's two underscores there. Init underscore underscore. And then you're going to do self. Okay, remember that's just Python. In Python, you use the self parameter, okay, to indicate, you know, that that's the object. Inside this init function, you are going to initialize the inherited class nn.module. So you're going to do super. That's the inherited class dot init. So it's basically like you're initializing your own class, and you're also initializing the inherited class. Yeah, go ahead.
Is this like object-oriented stuff?
Yes. This is exactly what I said. This is object-oriented. Okay? Let me tell you why. Let me convince you of why. You want me to write this neural network with just 3 lines of code. Probably. But as these algorithms get more complicated, if you wrote it like that, it'll become incomprehensible. It'll become very confusing. Do you see? Let's say that you have to build a CNN, right? A CNN may have 6 things that it does, and then you need to have multiple CNNs, one after the other. So your code will become very long and very confusing. But if you take an object-oriented approach, what you can do is you can define certain classes. For instance, you can define a class called, let's call it head for now. The class head, right? Which is made up of a lot of things. And then let's say that your model requires you to use 8 heads. So then you would have to write 1 head and the code for the, and that would be very complex. Or you can just do something as simple as for I in range oops, sorry, 6, right? And this is a list comprehension where you just instantiate head 6 times. And so effectively you can leverage that. Do you see what I'm saying? So you can take one, and actually the head actually takes in an X input, for instance. So it makes it a lot easier so that in one line of code, you can instantiate one class called head, this one, which could have tons of lines of code here, 6 times with one statement. That's the beauty of this, if that you can do this later and it makes your code later a lot simpler. Do you see that? That's what object-oriented programming does for you anyway. But anyway, we're not doing that. Currently, we're just basically learning this basic template, and it's always going to be the same, okay? It's always going to be very consistent, okay? But yes, so I'm defining the multi-layer perceptron. As I said, the first time this looks really hard, we're going to do it so many times that then it's going to look, a lot more accessible. So now that I've initialized the superclass, right, and the class, here we need to define the objects of the neural network. So in this case, I'm going to build a multi-layer perceptron, okay? So I'm just gonna say here, define the layers for now. We need to come back to that function. I'm also going to specify the second function, which is where you perform the inference. So I'm going to say here, perform the inference, okay? So this is going to be another function called forward that takes in self, and it also usually takes X. Now they can take more parameters, but at least it needs to take X. This is the equivalent of the Y equal WX plus B, okay? This is basically where that is actually happening, okay? So now that I have my 2 functions, this function will end with a return. That return is the result of the neural network. So let's just do an example. That's probably the best way so that you can see how to build a multi-layer perceptron, okay? So we're going to build this. Initially, I'm going to build this for Iris, just so that it's consistent with the previous example. So Iris will have, the input is 4, right? So, and then we did 4, 6, and 3. So I'm going to do that. So I'm going to create self dot linear 1. And here, this is a variable I'm creating, so it can be lowercase, linear 1. But I'm going to instantiate it to be an nn.linear, and that's what's important. Remember, this is what I said here, that this equation is actually nn.linear. Okay? All right. So remember how we needed to define the shapes of W, basically? That's what you need to define here as well. Okay, so nn linear. We know that the first layer has how many neurons for Iris? The input? The input. 4. Very good. There you go, 4. And the next layer, the hidden layer, had how many neurons? 4, then 6, right? So if we go back to the whiteboard, unfortunately, I have to switch between. So I'm building, once again, I am building that one. I'm building this one, right? So I have 4 neurons in the input layer, 6 neurons in the hidden layer, and then 3 neurons in the output layer. Do you guys see that? So that's literally what I'm doing. Just like I did with the matrix multiplications, I'm just switching that to be the nn.linear because nn.linear does that for you. It's just a class. It's a wrapper, basically, that PyTorch created around that Y to make things more convenient. Everyone with me? So now let's go ahead and define that. So I'm going to go here. I'm going to do 4, comma 6. There you go. All right. Then what else do I need? I'm going to need the next layer. So I'm going to call it self.linear 2. And that's going to be equal to an nn.linear. And that, you guys should know this. What goes here? I'm going from hidden 1 to the output layer. Well, but 2 values are needed here. If this is 4 to 6, then this should be 6 to, well, I'm only building the multi-layer perceptron. So yeah, you're right if you're building the deep learning one, and we can do that too. So here should be 6 to 3. Do you guys see that? Should do this. That's it. That's how PyTorch works. And you understand that this is the underlying is that Y equals WX plus B. Okay? Now there's other things that I haven't added yet. So the model that I'm building is a neural network that is a linear model. Doesn't have the power of actual neural networks because actual neural networks need to have something called activation functions, which is what adds the nonlinearity. I will cover this in a later lecture, all right? But I just want to give you the overall architecture so far. So believe it or not, that's it, right? So this is very simple. So now in the init class, you just really like define things. So this is the place where you would, you could say like, batch equal 32. It's a place where you define like variables, constants, right? So here we're just instantiating the objects, but we haven't actually created the architecture yet, okay? The architecture will be created in the forward function, but using linear 1 and linear 2. So now it's very straightforward. We go down here to the forward function, and we know that the input is x. So what is this x? The vector of 4. But that could also be a matrix of 150 by 4, or 30 by 4, or 12 by 4. As long as it has the 4 columns, it doesn't matter the number of samples, the batch size. Okay, so now let's go ahead and build the actual architecture. So there's a lot of ways of doing this. I usually just like to do this. So now notice I'm doing self dot linear 1. And the input to this is x. So what is that? That's basically the x multiplied times the first w to produce hidden 1. This part here is equivalent to just this, I did this part until here. And now I need to do the second part, right? So it's going to depend on the output. So the way that it's done, go over here. Okay, so I've done that. It's basically transformed. And so now I'm going to take the result of this, right, and make it I could have called this H1. I mean, there's no reason why, you know, it's just being replaced. But I usually don't do that because why? You know, what I mean? But I could, I mean, if I would be, it was being more like correct, I guess I would do this. And then I'm gonna do y equal self dot linear 2. This is really important because remember that the dimensions are there and you have to take account of those dimensions for this to work. So now this would take what? H1. Do you guys see that? Does this make sense? And then the result, that's it. That's all it takes to build neural networks. And for the rest of the you know, this sequence, we're gonna build them like this. Always. What's gonna change? We're gonna have more of these as we make it deeper, right? Which means we're gonna have, you know, the architecture is defined in the forward function. So these things are gonna change basically. But we're basically always gonna have, for the sake of this class, going to have an init function and a forward function. So now you might be asking, okay, so how do you instantiate this? Okay, that's the next part. So this is the class definition, right? And it accepted it. I don't have any data yet, so I can't really run it through data, but I can instantiate this now by doing the following. It is a common practice to use the keyword model, okay, to designate the actual model. And then this is just an instantiation as in classic object-oriented programming. So the class is called MLP underscore net. So we would just do that, and that's it. As you can see, model the class has been defined, and now it's been instantiated. And that's basically it. That is your neural network. That's it. Not that difficult, right? And basically what we're going to continue doing for the rest of the semester is just playing with these architectures and making them more deeper, more complex. As I said, these are still just linear models. We have to learn, but I need to give you some intuition as to what that means. And obviously I haven't added the optimization part yet. Any questions? No questions? Does this make sense? So this is how you would use the models, right? So you would now, let's say you want to do a prediction. So what would you do? Well, you create something ypred, call model, oops, sorry, equal, you call model, and you give it an input here. So you're going to call it like X, X. That's it. However, one important thing is when you're using PyTorch, everything needs to be torch. So you can't just create a NumPy vector and feed it into torch. It's not going to work. It's going to like complain about it. You have to convert it to a torch tensor. You guys see that? So you have to, so basically, we could try something. Let me see. Like, X equal torch dot rand n, right? And then the shapes were, what shape should this be? Let's say 1, 3, right? So I'm going to do X dot shape. Okay. Didn't like it. Mat1 shapes cannot be multiplied. 1, 3, 4, 6. Oh, yeah. It's not 3, right? Not 2. Who can tell me? I made a mistake here. What should this be? I'm using it as the input to the neural network. What is the size of the inputs of this neural network? Yeah, yeah. 4 and 6. It's iris, so it's 4. Right? So that's the size should be 4. Does that make sense? So now hit run. There it is. This time it didn't complain. Y Fred dot shape. What would you expect this to be? 1,3. It's the exact same exercise I just did, right? So it's literally this one. You see how I did this exercise, right? And I printed the shapes. And now I've repeated the same thing, but using like the more sophisticated approach of Torch. So I gave it, I can also give it this one, right? So I can give it a batch of 54, right? So, and I should get what I'm looking for. So let me try this. I'm gonna say this, but I'm gonna call this one XB for batch. So I'm assuming it's a batch of 50 samples of size 4. Do you guys see that? This will also work. Okay, I'm gonna run it through my model. But, you know, this should be XB. Let's just change this to be YPred B to indicate the batch. Okay, it worked fine. If I print the shape, what's this shape? What is the what will be the shape of this matrix or tensor? 150 by 3, right? Exactly. There you go. Like magic. That's it. It's the same thing we did before, only with PyTorch. Now, is this a PyTorch linear neural network? Yes. Is it predicting correctly? No. Why? Because all the weights currently are random values. When you do this operation over here, you define this, you know, remember, we are inheriting the NN module class. The beauty of that is that it takes care of all those initializations. Inside, it initialized the W's, it initialized, you know, everything with random values. But the nice, very cool thing about this is we've built an architecture that takes inputs and produces outputs. They're just not correct yet because we haven't trained this neural network. That's the next step. So in future lectures, we're going to start using this function, but training. Got it? I definitely strongly recommend, I think it's 7:38, so it's probably stopping time. I strongly recommend you go back to the lecture from last week where I did everything on the board. Do you remember? Practice that by hand. Do it by hand. Then, many times, do this script, right? By hand, or not by hand, run it, do the code, then repeat this with this approach. So for instance, one nice exercise that I would recommend you guys do is not homework, but in this example, we built a neural network with 3 hidden layers. Remember? We did the input H1, H2, and H3. That's reflected here. H1, H2, H3, right? We did it. You can totally do that here. Just create a new class, call it 3 hidden DL network, and then just do it here, and you should be able to build that exact same. Any questions, guys? All right. So this is, honestly, this is like very important. practiced this a lot. We're gonna continue with this example, probably train Iris since I already started with Iris. The next step is gonna be to define the training function, the loss function, so that we can actually learn the weights, right? And measuring performance of this model. So we'll do that in the next, it's 7:40. So we'll do that in the next class. So I'll stop it here.